Merhaba arkadaşlar. Umarım iyisinizdir. Geçtiğimiz haftalarda işletim sisteminin tanımından, işletim sistemlerinin genel konseptlerinden bahsettik çoğunlukla. Genel bir girişin ardından. Artık bu hafta proseslerden bahsetmeye başlayacağız. Eğer bir sorunuz yoksa doğrudan başlıyorum. Var mı sorusu olan? Yok sanırım. O zaman başlayalım. Okay. As you know already, early computers allowed only one program to be executed at a time. This program had complete control of the system and had access to all the system resources. But in contrast to that, our modern systems allow multiple programs to be loaded into memory and executed at the same time. This evolution resulted in the notion of a process, which is a program in execution. A process is the unit of work in a modern computer system. And finally, this week, we are going to start to discuss processes. As we mentioned earlier, a process is a program in execution as an informal definition. The status of the current activity of a process is represented by the value of the program counter and the contents of the processor's registers. The memory layout of a process is divided into multiple sections. These sections include text section, which includes the executable code, data section, which includes global variables, heap section, which is the memory that's dynamically allocated during the program runtime. Stack section, which includes temporary data storage when invoking functions, such as function parameters, return addresses, and local variables. So basically, we can say that we have text section, data section, heap section, stack section on our on our processes. Here you can see an abstract of a process in memory. We have text, we have data, also we have heap and stack sections which can grow by execution time. We highlight that a program by itself is not a process. A program is a passive entity, such as a file containing a list of instructions stored on the disk. We generally call them as executable files. In contrast to that, a process is an active entity with a program counter specifying the next instruction to execute and a set of associated resources. A program becomes a process when an executable file is loaded into memory. We have two common techniques for loading executable files, which are double-clicking an icon representing the executable file and entering the name of the executable file on the command line. Although two processes may be associated with the same program, they are still considered two separate execution sequences. For instance, several users may be running different copies of the mail program, or same user may invoke many copies of the web browser program. But each of these are a separate process, and although the text sections are equivalent, the data, heap, and stack sections will be different on different instances of a same program. Here we have a beautiful figure. This figure shows here and illustrates the layout of a C program in memory. So highlighting that how the different sections of a process relate to an actual C program. This figure is similar to the general concept of a process in memory, as we mentioned, with a few differences. The global data section is divided into different sections for initialized data and uninitialized data. And also a separate section is provided for the parameters passed to the main function. So actually, this part is text, this part is data, and we have heap and stack. As you can see here, we have two different sections for data. Sorry. Initialized data will be stored in this section, and uninitialized data will be stored in this section too. Also, we have heap section to dynamic stored variables, and we have stack for our regular variables here. So this is how we can store a C program in our memory. So it's very similar to a general process concept. For that reason, it's a beautiful example of how we can describe processes. As a process executes, it changes states. The state of a process is defined by the current activity of the process. A process may be in one of these states: new, running, waiting, ready, and terminated. New means the process is being created. Running means instructions are being executed. Waiting means the process is waiting for some event to happen, such as an I/O operation or reception of a signal. Ready means the process is waiting to be assigned to a processor. And terminated means the process has finished its execution. Here you can see the diagram of process states. These names are arbitrary, so they can be changed, that they may change across the different operating systems, but the states that they represent are found on all systems. It's important to realize that only one process can be running on any processor core at any instant, but many processes may be ready and waiting. So that means, let's assume that we started a new program. So that means a new process is created, but it's not associated with any operation. It's just created. So that means it's a new process. After that, when that process gets its resources, it will be ready to execution. So that means the state of process changed to ready. But there could be lots of different ready processes, and a scheduler dispatch needed here. CPU needs to decide which process will be executed next. So based on that, let's assume that a process selected from the processes which states are ready. So that means we can just execute only one process at a time on a single core CPU. On that case, the state of that process will be running. In some point, that process can need some I/O operation. So that means its state will be changed to waiting. Or based on the clock, we can interrupt the execution of that process. So that means its state will change to ready. Also, it's possible to complete its job during the running state. So that means we are going to terminate that process. So in that case, the state of process will be terminated. So this is how the process can change their states based on our process states. We have new processes, ready processes, running, waiting, and terminated. It's important to understand that, again, I have to repeat that only one process can be running on any processor core at any instant. Okay, now we're assuming that we have just a single CPU with a single core. So that means we can only execute just one process on any processor core at any instance. So that means only one processor state will be running in a time. But many processes may be ready and waiting. Okay, so this is the key point of the understanding of process states. Let's continue with the process control block. Each process is represented in the operating system by a process control block, or we can call them as PCB. Also, it can be called as a task control block. A PCB can be shown in this figure. As you can see, it contains many pieces of information associated with a specific process, including these ones. Process state, the state may be new, ready, running, waiting, and so on. We already know that. We have a program counter in process control block, which is the counter indicates the address of the next instruction to be executed for this process. We need CPU registers. The registers vary in number and type depending on the computer architecture. They include accumulators, index registers, stack pointers, and general purpose registers, along with the program counter. This state information must be saved when an interrupt happens to allow the process to be continued correctly after when it's rescheduled to run. Also, we need CPU scheduling information. That means this information includes a process priority, pointers to scheduling queues, and another scheduling parameters. We need memory management information. This information may include such items as the value of the base and limit registers and the page tables, depending on the memory system used by the operating system. We need accounting information. That means this information includes the amount of CPU and real time used, account numbers, job or processes numbers, and so on. And the last one, we need IO status information. This information includes that list of IO devices allocated to that process. It could be a list of open files and so on. So in brief, the process control block simply serves as the repository for all the data needed to start or restart a process, along with some accounting data. So you can get to all information about your process based on its process control block. Every process has a process control block, and on that block we have lots of different information based on that process. Some of them are process state, program counter, the registers used by that process, memory information used by that process, IO information used by process. So based on that information, we can start that process or restart that process based on the states, based on the queue on the state chains. The process model we discussed so far has assumed that a process is a program that performs a single thread of execution. For example, when a process is running a word processor program, a single thread of instructions is being executed. Most modern operating systems have extended the process concept to allow a process to have multiple threads of execution and thus to perform more than one task at a time. This feature is especially beneficial on multi-core systems where multiple threads can run in parallel in different cores. So we're going to discuss the details of threads in the next chapters. I'm going to continue with the processes. The objective of multi-programming is to have some processes running at all times to maximize the CPU utilization. The objective of the time sharing is to switch a CPU core among processes so frequently that users can interact with each program while it's running. To meet these objectives, the process scheduler selects an available process for execution on a core. Balancing the objectives of multi-programming and time sharing also requires taking the general behavior of a process into account. In general, most processes can be described as input-output bound processes or CPU bound processes. An input-output bound process is one that spends more of its time doing input-output operations than it spends doing computations. A CPU-bound process, in contrast to that, generates input-output requests infrequently, using more of its time doing computations. So we need some queues to schedule that processes. As a process enters the system, they are put into a ready queue, where they are ready and waiting to execute on a CPU's core. This queue is generally stored as a linked list. A ready queue header contains pointers to the first process control block in the list, and each process control block includes a pointer field that points to next process control block in the ready queue. The system also includes other queues. When a process is allocated a CPU core, it executes for a while and eventually terminates, is interrupted, or waits for the occurrence of a particular event, such as the completion of an I/O operation or I/O request. Processes that are waiting for a certain event to happen, such as an I/O request, are placed in wait queue. So we have different queues on operating systems. Your newly created processes will be stored on the ready queue, and if your process is ready and then start to executing on the running state, and then in some point start to wait an I/O request, so that means that process will be located on the wait queue. So we generally create these queues using linked lists. Every element of that linked list is a process control block, and every process control block shows the next element on the queue as another process control block. A common representation of process scheduling is a queuing diagram, such as that in this figure. Two types of queues are present: ready queue and a set of wait queues. The circles represent the resources that serve the queues, and the arrows indicates the flow of the process in the system. So we have CPU, we have I/O, these are the resources, and the arrows show the flow. A new process is initially put in the ready queue. It waits there until it's selected for execution. Once the process is allocated a CPU core and is executing, one of several events could happen. The process could create an input-output request and then be placed in an input-output wait queue. The process could create a new child process and then be placed in a wait queue while it awaits the child's termination. The process could be removed from the core by force as a result of an interrupt or having its time slice expire and be put back in the ready queue. So a process on the system could be on a ready queue or wait queue, and we can create different wait queues for different operations. A process continues this cycle until it terminates, at which time it's removed from all queues and has its process control block and resources deallocated. So that means that process gets its job done and is terminated. So this is how we can represent a process scheduling scheme as queues. So basically, we can say that a process moves between the ready queue and various different wait queues during its lifetime. The role of the CPU scheduler is to select from one of the processes that are in ready queue and allocate a CPU core to that process. As we mentioned before, interrupts cause the operating system to change a CPU core from its current task and to run a kernel routine. Such operations happen frequently on general purpose systems. When an interrupt happens, the system needs to save the current context of the process running on the CPU core so that it can restore the context when its processing is done. Essentially, suspending the process and then resuming it. The context we described here, actually presented in the process control block of the processes. Switching the CPU core to another process requires performing a state save of the current process and a state restore of a different process. So basically, we are going to change the context. We are going to remove a process from the CPU and we are going to load a new process. So basically, it's called as context switch. And this task illustrated in this figure. When a context switch happens, the kernel saves the context of the old process in its process control block and loads the saved context of the new process scheduled to run. So as you can see, and as you can guess actually, there could be some idle time on CPU while we are operating that context switch. Context switch time can be described as pure overhead because the system does no useful work while switching. It has to wait the complete of switching to execute that process again. So switching speed can be differ from machine to machine, depending on the memory speed and the number of registers that must be copied. So having lots of registers can be considered as a good indicator of performance. But also that means when you have to make a context switch, you have to copy lots of different registers. So it's going to consume more time. But a typical speed can be measured by microseconds. The processes in most systems can execute concurrently, and they may be created and deleted dynamically. So these systems must provide a mechanism for process creation and termination. In this section, we are going to explore the mechanisms involved in creating process and illustrate process creation on Unix or Linux systems. Maybe we can consider the Windows systems too. During the course of execution, a process may create several new processes. As we mentioned earlier, the creating process is called a parent process, and the new process are called the children of that process. So basically, we have parents and children. Most operating systems, including Unix, Linux, and Windows, identify processes according to a unique process identifier, or PID, which is typically an integer number. Process identifier, PID. The PID provides a unique value for each process in the system, and it can be used as an index to access various attributes of a process within the kernel. So if you have a unique identifier for a process, that means you can use that identifier to access its process control block and access its information, its attributes. In general, uh, when a process creates a child process, that child process will need certain resources, such as some CPU time, some memory, some files, some input-output devices to accomplish its task. A child process may be able to obtain its resources directly from the operating system, or it may be get a subset of the resources of the parent process. The parent may have to partition its resources among its children, or it may be able to share some resources, such as memories or files, among several of its children. When a process creates a new process, two possibilities for execution exist. The first one, the parent continues to execute concurrently with its children, and the second one, the parent waits until some or all of its children have terminated. So this is the basics of process creation. Is that clear? Do you have any question about the basics of resource sharing and execution options? Okay, then. There are also two address space probabilities for the new processes. The child process is a duplicate of the parent process, so that means it has the same program and data as the parent. And the second one, the child process has a new program to load it into it. Okay, we have a parent process. That parent process is going to create a new process, a child process. A child process can be duplicate of the parent process, which created by, or it can load a different program. To illustrate these differences, let's consider the Unix operating system. In Unix, actually, please do not forget that while I'm considering Unix, that includes Unix operating systems, Linux operating systems, and Mac OS operating systems. Okay, they all use POSIX API, so that means in this manner, when I said Unix, you can easily understand that I'm considering the Unix-based operating systems, which includes Linux and macOS, just not Windows. Okay, so in Unix, as we have seen, each process is identified by its process identifier, which is a unique integer. A new process is created by the fork system call. So you can use fork system call to create a new process. The new process consists of a copy of the address space of the original process. So that means when you fork a new process, that means you created a copy of your parent process. These mechanisms allows the parent process to communicate easily with its child processes, because communication between processes is an important topic about while considering the processes. Both processes, the parent and the child, continue execution at the instruction after fork, with one difference. The return code for the fork is 0 for the new child process, whereas it will be non-zero process identifier of the child is returned to the parent. So you can see you can see that specification from this figure. We have a parent process. We created a new process, a child process using fork. So here, the process ID of our child is 0. They are exactly the same processes actually, but the main difference here, parent has a process ID, but child process, the ID of child process will be 0. So based on that, okay, they're going to continue to execution concurrently, but you can easily identify them. Okay, this is our parent process and this is our child process. After a fork, actually fork system call, one of the two processes typically use the exact system call to replace the process memory space with a new program. So that means if you are going to load a new program to that child process, you have to use exec system call. The exec system call loads a binary file into memory. So that means destroy the memory image of the program containing the exec and starts its execution. In this manner, the two processes are able to communicate and then go their separate ways. The parent can then create more children, or if it has nothing else to do while the child runs, it can issue a wait system call to move itself off the ready queue until the termination of the child process. So this is how the process creation works on Unix-based operating systems. And here we have an example. The C program shown in this figure illustrates the Unix system calls previously described. We now have two different processes running copies of the same program using fork. The only difference is that the value of the variable PID for the child process is 0, while that for the parent is an integer value greater than 0. So using that mechanisms, we can execute our child process and parent process using the same code. So here, this is a simple C program. We have to include types.h and unistd.h to use PID and fork comments. So using PID type, we can create a new PID, process identifier. And using that process identifier variable, we can fork a child process. So in this point, when we fork a child process, we have a parent process and we have a child process. They're executing the same code, but we have just one difference. The parent process has a unique process identifier, but the child process has 0 as process identifier. So if process identifier is less than 0, that means we have a problem. We have encountered an error. Else, if the process ID is 0, that means we are executing the child process now. But if we have a non-zero process ID, that means we are executing the parent process now. And we can create a wait command on parent process to wait the termination of child process till the end. So this is how you can use how you can create your own child processes with a simple mechanism on your own C programs. So basically, that's a user application. That's not the part of operating system. We just considering that here, we can use some system calls to communicate with the operating system to create our own processes. Okay, so this is just a user application. You can write this program on your own computers. A process terminates when it finishes executing its final statement and asks the operating system to delete it by using the exit system call. So basically, exit system call means, okay, this process is going to terminate. At that point, the process may return a status value, typically it will be an integer 2, to its waiting parent process using the wait system call. Basically, if the parent use the wait system call, that means it waits the termination of the child process. So child process has to send a message to parent process when it's going to terminate it. So all the resources of the process, including the physical and virtual memory, open files, and I/O buffers, will be deallocated and reclaimed by the operating system. A parent may terminate the execution of one of its children for a set of reasons, such as this. The child has exceeded its usage of some of the resources that it has been allocated. The task assigned to the child is no longer required. The parent is exiting, and the operating system does not allow a child process to communicate if its parent process terminates. So in that cases, parent process can use the abort system call to terminate its own child. Some systems do not allow a child to exist if its parent has terminated. In such systems, if a process terminates normally or abnormally, then all its children must also be terminated. This phenomenon, referred to as cascading termination, is normally initiated by the operating system. A parent process may wait for the termination of a child process by using the wait system call. We already know that. The wait system call is passed a parameter that allows the parent to obtain the exit status of the child. This system call also returns the process identifier or the terminated child so that the parent can tell which of its children has terminated. When a process terminates, its resources are deallocated by the operating system. Again, we already know that. However, its entry in the process table must remain until the parent calls wait, because the process table contains the process's exit status. A process that has terminated but whose parent has not yet called wait is known as a zombie process. All processes transition to this state when they terminate, but generally they exist as zombies only briefly. Once the parent calls wait, the process identifier of the zombie process and its entry in the process table are released. Now, consider what would happen if a parent did not invoke wait and instead terminated. So in that situation, there could be some leaving its child process as orphans. So the term orphan has used for that situation. Okay, we are going to continue with the inter-process communication, but before that, do you have any question? Are you clear? Okay, then. Before moving to inter-process communication, let's take a break. I'll be here in 10 minutes. See you.